Now let's review the memory system model, and we'll start with the API approach. Okay, because we are computer science people, we understand software and APIs more than the hardware at this stage. So let's tackle this problem or understand this problem, understand this component from an API perspective. Okay, let's say there is an API which is called memory 1K for some reason. It takes like 4 parameters, and one is a parameter by reference. So this is written in C. For Java everything is passed by reference, I believe, or may not be, but this is what the reference in C language is. But anyway, this is a reference value, and these are the passed by value argument. Okay, so we pass our intention to this memory API, that whether I want to read or write into that through that API. Let's say I want to read from this given index, okay, or we call it address in terms of hardware, but let's call it an index here. Then this API will give me back the integer value stored at that specific index. Okay. Now let's say if I want to write, so I set this read to false and write to true, and we pass it and certain index, and then what this API will do, it will write this information passed in this variable into the given index. Okay, so that's the memory functionality. How it is implemented in C, we let's say implemented like this. Okay, we have a static memory like an array of integer of 1024, which is 1 key information storage, and then we compute I as a modulus operation of given index to 1024. So this is like just a fancy thing to not to check if index is more than like this array boundary or not. We just like given index, whatever the value is, we give a modulus operation and get that. Basically I then will have a range, surely have a range from 0 to 1023. So we never will access out of bound from in this specific array we define. But that's a kind of software trick there. But anyway, the function it will give, it basically takes this I or index value and check if the read operation is intended, read and not write. Then what it will do, it will read from the array, this memory, and write it into the variable info. Okay, so that's basically we are getting or reading the data from the storage. Okay, otherwise if it is not read and write, then whatever value is passed in the info is written back into that index position of that integer array. Otherwise no operation is done when we return. Okay, so that's the concept of any memory. So what my interface diagram would look like for this hardware component would be like, let's start with a box. We don't know what is inside and how it is implemented. Just like an API, when we give an like header file includes some library function, we only know how to call it. We don't know what inside it, right? So this is the interface diagram. We don't know what inside it, how to implement a memory. But interface wise, let's say I have two signals. So this is single bit signal, read, write, okay, an index of like 10 bits, okay. Why it is 10 bits? Because 10 bit is enough to encode value from 0 to 1023. So we don't need more bit than 10. Okay, so we don't need 32 bit. We just need 10 bit to represent an index value between 0 to 1023, and that's sufficient for this piece of hardware. If we are making an 1K storage, okay, 1K storage, and it's now. On the other hand, we have a bidirectional info signal. Why this bidirectional? Because either we can read from the memory, which go out as an information, or we can write into the memory. So your information flow in two directions, and that's why it's bidirectional, and this information is 32-bit, like integer is 32-bit, for example. So this is the interface diagram, and we can simplify that as instead of drawing the big arrows, we can have just one arrow with the bus notation of 10-bit for the address, and data is bidirectional. Okay, these are 4 signals that we have seen in this interface diagram. There are more to it. One is the reset signal. Okay, reset is important signal when we turn these, let's say, from 0 to 1. All the content, the conceptual array inside this memory, all this content will be erased out and be replaced with 0. Everything is wipe out. Okay, and most importantly, it takes a clock signal, a reference clock signal, based on which the function happens inside the memory. And this timing diagram represents the function of the memory, at least part of the function of the memory, right? Okay. So now what is, let's look at this thing, right? Clock goes forever, right? And this is one clock cycle, like one transition to high to transition to low. So in previous clock subsystem module, I represented the clock as a trapezoid signal to represent really what the clock look like, because it takes some finite time to rise from 0 to 1. But in most of the timing diagram, you will see that it is drawn as a squared signal. Okay, squared signal, because this is to simplify the situation, and we all know this is not the real case. It has some rising time and some falling time and so on and so forth. Okay, but anyway, so we represent clock signal in most diagram as square signals, okay, or rectangular signals, and this is one cycle. This is one cycle. This is another cycle. So we usually measure it from high to high transition to high transition time edge. So this is one clock cycle. We don't usually measure from low to low. Okay, there is different reason for that, but not relevant in this discussion. So what happens is this. Now the reset signal, this is the input signal. So we are saying that at T1 time, we make it up to logic 1 and keep it that for one clock cycle and make it down, and then it will stay down for rest of the operation, right, in this example. And this is my reset cycle, means during this time period, my memory will get wiped out and every content will become 0. Okay. Then let's say we have some read and write, some storage, etc., etc. And then we are doing some read operation starting at time 2. So we make that read signal up, keep the write signal to logic 0. That's my read configuration. And we send the address, 10-bit address, to the address bus. Now you see there is a dotted line here. What does it mean is that this is a signal, but this value is, we don't care. We don't know, we don't need to know, that kind of thing. We only want to know that at T2, this signal, whatever previous value was, has been changed. So this is kind of a simplification from the previous diagram where we show that as a trapezoid signal, they're changing. Because we don't care about that value, we don't really need to draw them. Okay, we just give a dotted, okay, some value, and then I change and give an address. Okay. Since this is also an electronic component, it will take some time to process this request, my read request. Let's say it takes one more clock cycle. Like this one is when my request is placed, and then it will not produce the read data immediately at that cycle. It will take at least one clock cycle. Some memory takes more than one clock cycle to produce the data into the data bus. So in this example, what we are saying that I had some values on the data, but I don't care about that value. but at T3 this data is given back. Okay, so I produce in one cycle the read request, my data comes in the next clock cycle. Okay, so my read cycle really spans from T2 to T4. This is my read request cycle. This is kind of read request completion cycle. So I give the request to memory, next cycle it comes back. So this example, it takes one clock cycle, some memory takes more than one clock cycle. Okay, so that's my read. And then we want to do a write operation at T4 when I keep the read signal at 0 and write signal I make it up to logic 1. So this is write configuration, and I want to send the address. Okay, I send the address, and not only this time I don't need to send the address, I also want to send the data, what data to be written inside this memory. So I need to set up a data value on the data bus, which is, let's say, 0ABCD. So what will happen at the end of the cycle, this data will be stored inside the memory. Now here, one thing to observe very carefully. See, first of all, during the read signal, we don't need to keep the read signal throughout the end of the cycle, like T4. We can just take it down. Okay, or we can keep it, no harm. Okay, this example, took it down at T3, but we could keep it till T4 and then change it to 00B, for example. That won't change any functionality. We can keep it there. Okay, second point is that, can we do a request while this memory is being read, it's fulfilling this request? Can we have a back-to-back write operation initiated at T3? Okay, answer is no. Why no? Because, see, during the write cycle, you are giving 4 datas here: your read, write operations value, your address, and you need to put your write, whatever data you are going to write, on the data bus. But see, there is only one bunch of line there, right, used for both writing the data or get the data out. So if you want to place this ABCD under this during this T3 and T4, there will be some conflict, right? Your memory is going to write some data onto this bus, like 1, 2, 3, 4, and you are trying to write ABCD on the same bus at the same time point. So they will conflict and system will behave erratically, basically. Okay, so what this means is, you cannot perform a back-to-back read and write operation. Can I do a back-to-back write and write operation? Like, let's say on this cycle, after that, can I initiate another write where I keep the write signal as high, I send another address, I send another data? Absolutely, because we're not conflicting with each other. Can I make a write? Can I make a read after a write signal immediately after? Of course, because again, you are not doing anything that conflicts on this common data bus, right? Can I do a back-to-back read? Answer is yes. Why? Because see, if I doing a read signal here, let's say, forget about this is write. Let's say this was a read signal. This signal is high. This signal is low here, and you produce an address. Okay. So what happened? This request will be completed in the next cycle, right? So while during T3 and T4, your request of T2 and T3, that request being served on the data line, your request from T3 to T4 will be served at the next cycle. So there is no question of data conflict. Okay. Only restriction is a write immediately following a read, because your read operation takes some time to produce the data on the data bus, and you cannot contaminate the data bus during that time. Okay, so that's the simple concept there. So as a thumb rule, write immediately after read is no, we cannot do it. Everything else is possible. Read, back-to-back read, fine. Back-to-back write and read, fine. Back-to-back read, fine. Back-to-back write, fine. Okay, but not back-to-back read and write. Okay, so this is your memory system functional model. There are many complex other memory systems, okay, which is not relevant in our study, so I am not going to introduce you to those complex memory system which is really used in modern computer. But this is a very basic concept of how a memory works, what is the relation between read and write and timings, and etc. Okay, so now let's talk something about a very special type of memory. We call it a register file. Okay, so in previously what we have seen that we are reusing the data bus for both sending a data in or getting a data out. We can transform the design into this, like let's say there are like 32 register of 32 bit register. In that case, we can configure, instead of having an in out, we can have a special in, a separate in and separate data out. Data in and data out are separate. It is no longer bidirectional. Okay, and let's say address is 5-bit. Why? Because it's the 32 registers. You just need to encode 32 different addresses, which can be done with the 5-bit. So in this case, we actually solves the problem of back-to-back read-write. So in this case, we can definitely request a read, okay, and then immediately request a write in the next signal. Why so? Because your read request is produce your result onto data out, where for the next write you are actually giving memory the data through the data in, right? Giving memory to the data in. So there is no question of contamination, and we can do back-to-back read and write. Okay, so this is what the register file configuration would look like. It is simply another memory, but it's a small quantity memory. Instead of like having an 1 kilo 1024 amount of storage, you are just storing 32 of them. And instead of having a bidirectional data bus, we are having a unidirectional data buses, where one data is carrying the data input and other bus is carrying the data output. Okay, now we can modify this design into this design, and which is basically used in any processor we will be discussing about. Okay, so what happens, instead of having only one data out, it has now two data out with two read requests, simultaneous read request. Okay, and there can be possible simultaneous write as well. We'll see in later classes or lectures in this 147 and how it is implemented and processed. But point is that we are expanding based on, what we did, took a memory design, scale it to some smaller number of storage, and solve that read-write problem in our hand. Okay, we can do a back-to-back read and write so that we can make some fast operation needed in the register file component. And then not only one read, we are now trying to do two simultaneous read. Okay, So we can produce two different address and get the two different data read out of the register file. And we can do also a separate write address and separate data in. We can write the data back in the register file at the same time. It's possible. Now you might ask that why two output data out is needed, why two simultaneous read is needed in this component. If you think, like, most of the arithmetic and logic operations are binary operation, like two operand operation, right? Always like a plus b or 3 plus 4, 10 multiplied by 12, something like that. Like, it always involved two operands. Now if we had used this kind of register file, then we need to have two back-to-back read operation to access those two operands, right, stored in the register file. But in this design, we can just read them in one cycle. So that's a faster operation. So that's the reason, since most of the arithmetic and logic operations are based on two operands, so we better access them in the same cycle. So that's why these two data out are introduced, and also we can pass two different address from which we'll simultaneously read out from the register file. Okay. So this is all about your memory system model.